Alrighty, we are now on to chapter 3. So this is the stuff that'll be on your last exam, exam 3. So, my God. Sorry, do something with a toy because he wants attention. So now we're on to talking about exponents. And we've kind of talked about exponents before in terms of like bases are the same, exponents add, bases divide, exponents subtract, when exponents multiply, and stuff like that. So now we're going to talk about like exponential growth and decay and when the exponent is our variable. So what real world problems or examples do you think we can model with exponential growth or decay? So this is where then you guys would be like, oh, maybe this thing. Things that we can talk about with exponential growth and decay. There is, I don't know if you ever heard about radioactive decay, which helps us with carbon dating. So like figuring out how old some artifacts are. We also have like population growth. Specifically when we're talking about like bacteria or animals. We can also talk about decay in the medical field. So when you give a patient a dose inside of their body, it'll start using it up. So the amount that's just in their body decays away. So then to not overdose them, you need to figure that out. So you're not giving them too much medicine. Medical and stuff like that, right? There's like a lot. Alrighty, so modeling exponential growth, the growth factor. So exponential growth, exponential is modeled by a function of the form, right? F of x, it's pretty normal. Then we have this c times x, not x, excuse me, that was incorrect. C times a raised to the x. So now my variable is not like plus some other number or times some other number. It's up into the exponent. And we're talking about, oh, this is exponential growth, excuse me. And specifically, this is when a is greater than 1, and that's important. We'll come back to that in a second. All right, so the variable x is the number of time periods. Like, so specific, but this is in the case of talking about exponential growth. And we say time periods, not just meaning minutes, seconds, but also 3 days, 10 years, 5 minutes. Like we can talk about X in that terms, and then we'll talk about changing the time periods and so on. Okay, so 8a, the base, is the growth factor. C is the initial value. All right, and we can see that really quickly. If f of 0, it's going to be c times a to the 0. Anything raised to the 0 power is 1. So we're just left with c. So that's why it's our initial value. It's not like plus c. All right, so f of x, right, equals c times a to the x, has in general this shape of a graph. It's exponential growth, so we're going to expect it to grow. We're going to start at c, and it's just going to go up and up and up and up, and it gets faster and faster and faster. There's a fly near me. Okay, so let's go through some examples. So remember, x That is our number of time periods. A is our growth factor and C is our initial value. All right, so find a model for the following exponential growth situations. So I'm told exponential growth, so great. I know that it's gonna look like this. Of course it is, that's what we literally just learned. So a bacterial infection starts at 100 bacteria and triples every hour. So remember, C is our initial value, so C would be 100. And if it triples every hour, so every 1 hour time period, it's going to be 3 times more. So that means this is, let's do X. No, I want to put T for time. So X, C of X. So at 0 hours are passed, we're at 100. After the first hour, it's tripled. So times 3. So 100 times 3, 300. Okay. Now, after 2 hours, so 1 hour after is 300, it'll triple again. So after 300, now we're at 900. Okay. And then it will just continue on. So 900, not 900, yeah, 900 times 3 should be 2,700 and so on. So that's what we're saying, it triples every hour. So how can I use this type of function? So what do we think A is? So look at this. So 100, and then when X equals 1, it's 3 times 100. And then the next one is like 9 times 100. And then it's 27 times 100. Oopsies. Yeah, times 100. So 3 times 100, 9 times 100 times 100. Do you see that this looks like 3 to the 1 times 100, 3 squared times 100, 3 cubed times 100? That's where exponential growth comes from. And that's where that growth factor comes from, that 3. So looking at our model, well, there's X right here, all the way up right in this exponent. Perfect. So that goes ahead and tells me that A equals 3. If it said it doubles, then A would be 2. And it'd be nice and fun. So it'd be f of x equals 100. And then sometimes I'll put it in a parentheses just so it's clear that the 100 isn't involved with being raised to an exponent. So something like that. Okay. Okay, cool. So a pond is stocked with 5,800 fish. Each year, the fish population is multiplied by a factor of 1.2. So we're already told that's our growth factor, by a factor of 1.2. So I'm already given that C equals, 5,800 and A is 1.2. So we can just go over here and say that f of x equals 5,800, 1.2 to the x. Okay. So you notice, we'll talk about that in a second. I want to kind of talk about why can't, I talked about if it triples, it's 3 times. If it doubles, it's 2 times. Why can't it be 1? Why can't A be 1? See how A is, we would say like this is, I shouldn't underline it like that. We would say that is strictly greater just to really emphasize that it cannot be equal to 1. So A is strictly greater than 1. What if it equaled 1? Well, remember 1 to any power is just 1. So it's not going to grow. It's just going to be C the whole time. And we're talking about exponential growth, not exponential not doing anything. So that's not very interesting. It's not very fun. What's the point of studying? It's just going to be a number the whole time. It should be a constant function, basically. So it wouldn't even really have the same fun things that exponential growth and then exponential decay will have. So that's why A needs to be greater than 1. A also needs to be greater than 0. We'll talk about that in a little bit. And I want you to think about why. Think about if I had a negative number, what would happen as A? So, all right, cool. So we just did these two examples. So the growth factor, which is A, we just talked about, is the number by which the population is multiplied each time period. And I'm really, really sticking on that time period. I really just want to drill into your head that X is a time period. It could be 3 years. It doesn't have to be like 1 year, 1 second, 1 minute, something like that. So increasing X by one time period, we get f of X plus 1 equals A times f of X. So we saw that up here when I was, you probably can't see that, my little head's in the way. And when I just was trying to figure out, oh, if it triples every hour, oh, times 3, times 3, times 3, and so on. So thus, if I want to solve for A, because that's kind of like the hardest thing. Initial condition, fine, totally fine. But finding A, that was kind of the tricky part. So if I can just solve for A right here, so I divide each side by f of X, and I get this awesome equation to solve for f of X of X for A, which is called f of X plus 1 divided by f of X, right? So remember, this only works if I'm one time period above, not like the next one that's just shown on the chart. Like sometimes it goes 2, 4, 6, 8. I need like 2 and 3. Okay. But yeah, remember X is a time period here. And I really stress that because of this next example. All right. So Chinchilla Farms starts with 20 chinchillas. All right. C equals 20. Just going to start off by saying that. Let's highlight this so we don't forget about it. Oh, it's purple from our last class. After 3 years, there are 128 chinchillas. Assume the number of chinchilla grows exponentially. Find the 3-year growth factor. All right. 3-year growth factor implies what my time period is. Implies a double bar arrow like that usually means the word imply. It's not confusing enough that we have numbers. We have to have random symbols. So 3-year growth factor implies that X is in 3-year periods. So that's our time period, is 3 years. Okay. So it says after 3 years, you're like, oh, I'm going from 0 to 3. No, I'm going from 0 to my next time period, which is 3 years. Okay. So it'll basically be like, oh, here's X, here's f of X, and it would be like 0, 1, 120, 128. Because remember, X is in time periods. Ta-da. Okay. So find the 3-year growth factor. Okay, great. So I can do this with any X that I want. Just need to do the next one that's above it. So right, I want to find the growth factor. Oh, I didn't even need to say C was 20. Oh, not 120. Man, that was an exponential growth. Jesus. 20. All right. So remember A is f of X plus 1 over f of X. We have 0 and 1. So we're going to choose f of 0 plus 1 and f of 0, which is f of 1 and f of 0. Really just spelling it out. All right, we're going to go over here. So this is 128 divided by 20, which should be about 6.4. A good way to remember this is I need A to be greater than 1. If it's not greater than 1, it's going to be 0. So if I accidentally flip these around, well, then it's not going to be greater than 1. It's going to be a small number, which I don't want. So there we go. Okay. And that's how we can find the growth factor from just 2 points. Okay. Okay. So I think this should say growth rate. All right. So the growth rate of a population is the proportion of the population by which it increases during one time period. So it's a percent. No, yeah. It's the portion of the population which is increased during the old one. Okay. So It's similar to R, but it is similar to A, but it's not A. It's just similar. They're like siblings. Okay, so growth rate. So we like to call all of our rates R, and the equation for it, or do I derive this ever? Yeah, I don't. Okay. So the equation for this is f of x plus 1 minus f of x divided by f of x. Right? So it's the proportion of the population in which it increases during one time period. So I like to remember this by saying no row. This is like saying new minus old over old. This is called percent change. If you want to know, like, I think this is in chemistry, like the percent change or something, new minus old over old. So they also use this on Biggest Loser. My new amount minus my old amount divided by my old amount will give me my percent that I grew over that time period. Okay? Compared to what I started with. Well, what if we split this up into two different fractions, right? If I did kind of almost distribute this division, I would get f of x plus 1 divided by f of x minus f of x over f of x. What's f of x plus 1 over f of x? What does this look like? Well, that's just a, and this is just 1. So it's a minus 1. So that's pretty nice. So if I already know a, I don't really have to go through this long calculation. I can just subtract 1 from it, and I'm done. It's pretty nice. Okay? So 50 rabbits, ooh, tricky, they didn't put a number. 50 rabbits are introduced into a small uninhabited island. Crazy, rabbit island. 1 second. Whew. They have no predators and food is plentiful. Basically, they can just keep going, right? So the population grows exponentially, increases 60% each year. Okay, so I said new minus old over old. We call that like the percent change. R is a percent. Rates, interest rate. That's the only rate I can think of. But like rates are percentage. Okay, you think of rate also like miles per hour, but like rate in the term, like I'm thinking about something growing, like an interest rate. That's a percent. Rates are always going to be told to you as, oh, the rate or something is this or this percent. See a percent sign, read it carefully because it might be telling you something else, but most likely it's going to be a rate. Okay. Underline, I'm going to put rate. So increasing by 60% each year. So find a function p of x, x that models the rabbit's population after x years. Okay, so I start with 50 rabbits. So c equals 50. Great. Well, what about a? Well, remember that we said that we found out that r equals a minus 1. And r right here is 0.6. We kind of talk about rates as percentage, but when we're doing math with them, we really need to put them in decimals. So I'm going to put my 0.6 into this little cute little equation that we have. Remember, this equation comes from the definition of R. So this is just the definition of R, just a minus 1. And also we can say a is R plus 1, right? So a minus 1, so just add 1 to both sides. And we got 1.6 equals a. Great. So then I can go over here and put everything together. So I'll get p of x equals 50, 1.6 to the x. All right. Why do my x's look weird? Okay, great. And that's all we needed to do. So how many rabbits are there after 8 years? And now we're just going to go and plug in 8 for x, right? Because x is in years. Great. So 50 1.6 to the 8. I think one of you emailed me and was like, kind of, sometimes I don't put everything to my calculator. Is my phone dead? Oh no, thank God. But I'm not very good at, I'm a little lazy when it comes to my calculator typing. But now that we're doing stuff with exponents, things get really big and really small really fast. So decimals are very important. I like to hold out 4 decimal places. Last section, 2.7, I held it out to like, if it's like something 0, and then I'll hold up 4 after that 0. I don't know anything about sig figs. I took AP chemistry in high school 9 years ago. Couldn't tell you what a sig fig is. So I don't care about those. I just would recommend going out at least 4 decimal places. If I have something like 0, 0, 0, okay, then there's like a 0 here. Yeah, I'm going to go up 4 decimal places from there. Okay. But that's just a little tip. Okay. Just to make sure that you're getting something that's good. You can also just like put this all in one into a calculator. But if you're doing it bit by bit, you can also, it's fine to do it this way. Okay. So this will give me like 2, 1, 4, 7 and 4, 8, 3, 6. Oh wait, how many rabbits? Okay, I can't have that much of a rabbit. So then I would stop it there. I have to kind of think realistically how many rabbits there are. I'm not going to have half of a rabbit. But if I rounded it, I might get a little bit of a different answer. Okay, so rabbits. That's how many rabbits we're going to have, from 50 to 2,000. Invasive species. Okay, cool. So we talked about growth and how A needs to be greater than 1. Now we have like its evil twin, exponential decay. There is a show that I used to watch as a kid, and it was like, oh, not Rock Lee. It was like a karate fighter, and he had to find these little capsules, and he had 2 friends that were twins, and one can see all the good things and one can see all the bad things, and the girl that can see all the bad things was always happy, and that's like how I think about exponential decay. He also had to find these like little rocks, and he could like be a snake and be invisible. Oh man, if anyone knows what I'm talking about, please yell at me because I didn't watch that. Such a good show. Okay, so exponential decay is modeled by the function of the form. Oh, what do we think it's going to be? It's the same form, but now A needs to be between 0 and 1. Okay, growth greater than 1. Decay between 0 and 1. If it's 1, boring. If it's 0, also boring, because they'll just be constants the whole way through. 0 is even worse. It would just be 0. Wouldn't even be, initial value wouldn't be true because it would have to be 0. So why can't it be negative? Really gross. If I try to even think of like -1 to the x, it's not a continuous function because I can't take the square root. So even any like 1.5, any 0.5, it's just going to be, it's weird. Graph it, it'd be cool, but I can't have a negative as the base. It's just, there's no application to it. So we only want positive numbers for A. And if it's smaller than 1, it'll be decay, and if it's greater than 1, it'll be growth. All right, so now A, instead of being our growth factor, it's our decay factor, but it's still our factor. And A is between 0 and 1. The decay rate is R, which satisfies that fun little equation, A equals 1 plus R. So R is going to be negative, right? If A is between 0 and 1, and I have to add, right, also like R equals A minus 1. So if A is less than 1, and then I'm subtracting 1 from it, it's going to be a negative number, which makes sense because, right, R was like new minus old over old. My new is going to be smaller than my old. I'm decaying. So I'm subtracting a small number from a larger number, and then that's how I'm going to get a negative out. Okay. So, Oh yeah, that color. Okay. I couldn't think of what color it was going to be. So my decay, there's C, it's going to look like E. And it shouldn't ever go to 0. Unless it started at 0. Yeah. I'll just get really small. Okay. Right? Yeah, it'll just get really small. And small, but we mean close to 0. Okay. Oh, here we go. This is what I was talking about in medicine. So a patient is administered, he doesn't do it himself, DIY hospital, 75 milligrams of a therapeutic drug. It is known that 30%, that's a percent, why am I circling it? We highlight things, 30% of the drug is expelled from the body each hour. Okay, cool. So find an exponential decay model for the amount of drug remaining in the patient's body after X hours. Okay, so easiest thing, finding C. Great. Oh, let's write down our function. C is X, where C is 75. Okay. So, and we're looking for A. We're given a rate though. So we know that A is going to be R plus 1. Okay. And remember the difference between growth rate and decay rate and decay factor and decay rate, or just rate and factor. If you think of the word factor, A is before the R. Think about the word rate, R is before A. So that's how you can keep them up. If you want to just remember, if I see percentage, it's a rate, like an interest rate. And then R, rate starts with R, something like that. Okay. What else? Oh, so what is R now? Is R 30? No. 30% of the drug is expelled. So 30% is leaving. When we think about things slowing down, coming back towards us, like stuff is shrinking, negative. So R equals negative 0.3. We also know that because we're told to find the exponential decay model, and we just discussed about how R is always going to be negative. So I see a percent, smack a negative in front when we're talking about exponential decay. All right, so then we'll go over here and say A is 0.3, negative 0.3 plus 1. So A is going to be 0.7. So that f of x, I'm going to put everything together. 75, 0.7x. All right, I don't like that. There we go. And that is our decay. Right, so we're now going to use the model to predict the amount of drug that remains in the system's patient's body after 4 hours. So f of x equals 75, 0.7 to the 4. Oopsie. Okay. 0.24. I don't know why I wrote my 4. It's so weird. Times 75. And we get 18.007. And our initial condition is in milligrams. So that is what that's going to be. So that should be 4. So after 4 hours, we have 18 milligrams left. Pretty nice, right? Great. So we can also use decay for things like radioactive decay, which we also talk about as half-life. So half-life of radium-226 is 1,600 years. A 50-gram sample of radium is placed in an underground disposal facility and monitored. This is actually what they do. Savannah River National Lab, which is like an hour and a half south of here, I think also does, I think they do stuff with radium, but they have radioactive stuff there. And I think one of their big things is also getting rid of it. Same with Oak Ridge in Tennessee. So find a function that models the mass of radium after X half-lives. Okay, so lots of things. So first of all, half-life. I I think you guys learned about half-lives. I learned about them in high school, so I don't know if you guys did, and that wasn't in an AP class. Okay, so half-life is the amount of time it takes for a material to decay half of its mass. Okay, so we have a 50-gram sample after 1600 years, or one half-life. It's going to be 25 grams, right? So, so we know it's a decay, so A to X. C is going to be 50 grams, right? And so with half-life, what is it going to do? So X is in half-lives, not years. So X, B, F of X. So at 0, it's going to be 50. At 1 half-life, it'll be 25. At 2, it'll be like 12.5 and stuff like that, right? So we can find the equation for A and R have not changed at all, just now that we're talking about decay. So remember, A is going to be f of x plus 1 over f of x. So A is going to be 25 over 50. We also could have done 12.5 over 25. And that's just 1/2, which makes sense. Half of it is going away. So R would be negative 50. 50% of it's going away. Add 1 and you get 1/2. So that's cool. Half-life, oftentimes, when X is in half-lives, A is going to be 1/2. If X is in years and not half-lives, different story. And we'll talk about that in the next section, I think. I don't know. So now A is in 1/2. And I'm just going to say X half-lives, not years. Okay? Just really want to stinger that one in. So f of x is going to equal 50, 1/2 to the x. And some people also put it on the outside to show that the base is 1/2. Okay? Right? Use the model to predict the amount of radium remaining after 4,000 years. So x is in half-lives, not years. So f of x of f of 4,000, no. X is you're like, Mackenzie, like I get it. No, but I really want to make sure you do. It's like if I put 4,000 in there, it'd be like, oh, go change my oil, and I use olive oil. Sounds the same, very different. Okay, and really can screw you up. Probably won't kill you though, like that will. All right. So, how many half-lives are in 4,000 years? So remember, one half-life is 16,000 years. So one half-life for every 16,000 years (4,000 years) will get us 2.5 half-lives. Okay, so then I want f of 2.5, which is going to be 50, 1/2 to the 2.5. So 0.5 to the 2.5, which is, oopsies, Oh, that was right. Okay. 0.1768 rounded times 50. And this is going to equal 8.8388. What are my units? Grams? Okay. Grams. Just put a G. Okay. And that's how many grams you're going to be left for in 4,000 years. It's pretty crazy, but your half-life's really long. Okay. All right. So that is the end of 3.1. A lot of new things. So if you're a little confused, read the section in the chapter. I think it might be a little bit more useful. I think it has a little videos. Exponential growth and decay are pretty cool. We just have a lot of vocabs. Chapter 3 and chapter 4 are a lot of vocab things because it might not be things that you ever heard of before. Decay, exponentials, logarithms. So since this is the first section, while you're taking notes, also maybe just, I like to have a blank piece of paper next to me and I'll start like a definition things, which is really helpful with studying later on. And since exams are open book, open note, you can use them on your exam. You have all your definitions in one spot. Okay. So I will see you guys in the next section, 3.2. All right. See you there.